Swayam Prabha. Digital India. Educated India.
Hello everyone, we are now at the 10th lecture of this course, Fracture, Fatigue and Failure of Materials, and in this lecture we are going to discuss about the multiplicity of geometry factors, particularly for the determination of fracture toughness, and we will see that how based on the crack size, shape, position, how the value of K changes, or in other words the fracture toughness value changes. We will also see a specialized condition known as leak before break, particularly used in case of nuclear reactors, and how the fracture mechanics, the concepts are helping in developing this kind of condition. And we will see that how fracture mechanics is used in case of failure analysis in some real incidents. How can we use these concepts to generate the idea about the fracture toughness, or from this leak before break condition, how we can design various components. So, before we move on, as we have seen in the last lecture that whenever there is a fracture from the fracture surface itself, from the fractograph, it is possible to determine the fracture toughness at the point of fracture, and this is done typically considering the shear lip width. So, if this is the shear lip width, which typically occurs because of the plane stress condition, we can determine the shear lip width, and this is nothing but equivalent to the plastic zone size under plane stress condition, and that is given by d equals to r y is given by 1 by 2 pi K by sigma L strength square. In a similar fashion, we will see how this is employed in the real failure analysis, how this information will be helpful. So, this one here shows the fracture of a lab component, and what we can see here is development of some shear lip at this point, which is very clearly visible. And there are some other mechanisms that are also active, as you can see here the stresses for the fatigue crack growth bands. But for now we would see that for this particular fracture, considering the shear lip, how this can be helpful in generating the fracture toughness values. So, when this kind of failure occurs, we always check with the documents that are present to consider the various properties of the materials that are already established and that has been provided by the supplier. For example, in this case the yield strength of the material is quite high, it is a high strength steel of 1500 MPa. Fracture toughness of this material is expected to be 110 MPa root meter, and stress values at the point of failure is 830 MPa. Thickness is around 1.78 centimeter, and there is a through the thickness flaw which has a total length of 1.73 centimeter, and the shear lip depth is 0.8 millimeter. So, based on this we can figure out that whether the fracture toughness value at the point of fracture matches with the given provided fracture toughness or the expected fracture toughness values or not. If not, then there could be some other reason for failure that has led to the local enhancement in the fracture toughness values, or if it matches, then there could be some other reason, not the typical materials property that is of any concern. So, in this case let us use this shear lip depth value of 0.8 millimeter to see if we are finding out the K value. So, yield strength of the material is already known as 1500 MPa or 1.5 GPa. So, that leads to K value of 1500 square into 2 pi into 0.8 into 10 to the power of minus 3 and square root of that is giving us the value of K, which is 106.34 MPa root meter. So, that is what we are seeing here, and interestingly what we see is this 106 MPa root meter matches pretty well with the provided fracture toughness values, which confirms that it has satisfied this criteria. So, there could be some other reason which we can figure out based on the failure analysis. Okay, but we can at least say that there is no other defects or something that has led to change in the behavior of the material. The expected value is being met by the fracture toughness values that we can determine right from the fracture surface itself. Okay. Now, it has been said that there is a through the thickness flaw. Actually, this is considered as flaw in this case, but it actually is the design parameter which looks some kind of change in the geometry because of the design consideration, and that may have acted as a flaw. So, that total length is 1.73 centimeter. We can also figure out that what is the critical flaw length that would have initiated the fracture, that would have led the fracture. So, for that we can use the typical relation as K is y sigma root over pi a. Now, in this case y is 1 because it is a through the thickness flaw, and sigma is given as 830 MPa. What we need to figure out is the critical value of a, and K we have already estimated as 106. So, with this we can find out the value of A or AC, the critical value. So, that comes around 5.2 millimeter. So, if there was a crack of just 5.2 millimeter, that would have been sufficient to lead to this fracture, and instead we are having here a much larger or much longer flaw that have led to this failure. So, obviously, it has something to do with this flaw itself. And this the values that has been determined, K from this shear lip width is 106 MPa root meter, which matches pretty well, and the critical value of flaw size that led to fracture is 5.2 millimeter. So, the total length would be 10 millimeter, that would have been sufficient for fracture to occur. Okay. Now, along with that, we also need to consider the shape of the flaw. So, so far we have seen that there are notches which are either machined or change in the parameters of the geometry, which leads to a sharp crack, and for that we considered particularly the crack length or half crack length being A. In some cases we did consider rho, particularly for the calculation of stress concentration factor, but most of the cases, especially for stress intensity factor, we particularly rely on A as the primary crack or the notch or the defect dimension. Now, there could be also possibilities that this defect would not be this much of sharp, rather it can be an elliptical defect. For example, let us say a component which looks like this. Okay. So, instead of a surface crack, in this case we have a elliptical or a semi elliptical void. So, this is a semi elliptical, okay, which is having a total length for the major axis as C, and the minor axis, this is again the half length, and that is equivalent to A. Or in other word, we can have a component in which there is a through the thickness elliptical crack. in which case once again the major axis is 2C and the minor axis is 2A. So, in that case, along with the value of y being 1.12 or y being 1, considering that 2A by W is sufficiently less, we also have to consider another parameter which is another type of y. So, we also have to consider y2. This parameter is related to the shape of the crack, and in this case being elliptical. So, this is related to 1 by root over q, where q is the flaw shape parameter. We can see here these are practical values that has been determined for such different configurations of crack and the different positions of crack, and what we are seeing is this is A by 2C ratio is increasing with the flaw shape parameter. Now, when we have a crack of something like this shape, it has a natural tendency to form a semicircular or a circular void. Okay. So, let me draw it here itself. So, if we have a configuration like this, let us say this is the thing, and we are applying stress in this direction, So, it will try to form a circular shape. That means A equals to C, which obviously means the major axis and the minor axis being same. So, this leads to a spherical or a circular shape, and for that matter when we have this kind of circular shape, this is for the energy balance, anything tends to attain the spherical or the circular shape. So, for that we are getting the value of q as 2.47. You can see this has been experimentally validated also for this ratio of A by 2C to 0.5, we are getting a value of something like close to 2.5, something like 2.47 to be more specific. So, that makes 1 by root q equivalent to 2 by pi. Okay. So, this is what we are seeing, this y parameter, or this we often term as y2 in this case. So, this y2 parameter is root over 1 by q, and that comes to 2 by pi because it tends to grow to a circular one. So, as 2A by C tends to 0.5, q tends to 2.47 and y tends to, or y2 tends to 2 by pi. So, essentially that means that when we have cracks or defects of such shape and such position, we can actually have k, which is determined by multiplying this y1 and y2 along with this typical relations of sigma root over pi a. So, this y1 is based on its position. So, this could be 1.12 or 1. So, this is for edge crack, this is for center crack, we have already seen that, and sigma is the applied stress, pi a are all that we already know, and y2 is coming because of the shape of this defect or notch, and this is for the case of semi elliptical one, this is always 2 by pi because it tends to be a circular one. This is the same thing that has been shown here. Okay. So, based on this there are different kind of calculations which are typically done based on this defect size and shape and the position, so that we can predict the k value in a more accurate way. So, this is what is shown here. So, y1 as 1.12 for the case of edge crack and y2 is 2 by pi. So, this is typically for a semi elliptical or semicircular edge crack. Okay. Now, if we have a elliptical one, and in which case the C and the A are distinctly different numbers and it is not semicircular, but semi elliptical, in that case we often needs to find out the AC value. Okay. Now, AC here is not the critical one, but this is a combined one considering both the major and the minor axis, and this is given by square root of the product of the half major axis and half minor axis. So, this is half major axis, okay, because unlike a sharp crack or unlike a circular void, now we are considering a elliptical one. So, we have to consider their overall radius, which is given by a product of root square of half major and half minor axis. So, this is how the relation can be then formulated for an edge crack, where y 1 is 1.12, y 2 is 2 by pi, sigma is the applied stress, and AC is root over A dot C. Okay. So, this leads us to a very interesting mechanism of leak before break. Now, what happens in case of, particularly applicable for nuclear industries, in case of pressure vessels, when we have a cylindrical vessels in which the pressurized fluids are being kept. So, if there is any kind of cracks that generates on the inner wall of those kind of cylinders, that can lead to either a catastrophic failure or a leak before break condition. Of course, the leak before break one is preferred to avoid the catastrophic failure. Let me explain this in a more clear way. So, what happens is that, so let us consider a cylindrical pressure vessel, and in which there is a semi elliptical flaw on the inner surface of the pressure vessel, and let us say that this is the thickness. So, what happens is that there is a hoop stress that is being applied, okay, and as a result, because of this hoop stress, this crack is expected to increase its dimension. So, this is 2c, once again the major axis, and the minor axis is A. Now, what happens is that, as we discussed, that this always has a tendency to grow to a semicircular one, okay, just to minimize the energy balance. So, in that case, if it grows such that this A, or the length of the minor axis, which is now equivalent to the half length of the major axis, when it becomes equals to the thickness of the cylinder, then there will be leakage exactly at the point of contact between this crack faces as well as the cylinder wall. Okay. So, this leads to a leakage, and whatever pressurized fluid is stored inside the cylinder, that can come out from this, and there will not be any catastrophic failure. So, that although is a failure event, but that helps in avoiding the catastrophic failure. So, that is why leak before break condition is favored. So, in case of leak before break condition, actually the typical relation as K equals to sigma root over pi A, okay, the one that we have developed from the Griffith criterion itself, this is considered as sigma root over pi T, because at the leak before break condition, this A is equivalent to the thickness of the cylinder. Okay. So, to make the leak before break condition applicable, we have to see, we have to check that whether this A equals to T can be obtained, and still it should not exceed the typical fracture toughness value of a material. Okay. When we use a material for any kind of design, we first of all need to know the fracture toughness values of that, right, and this fracture toughness value means the plane strain fracture toughness value, which is supposed to be a constant one. Now, in practice, we need to also figure out that what would be under certain conditions, what would be the fracture toughness values, and whether that exceeds or whether that is less than the predicted value determined for different conditions. So, in this case, for this leak before break condition to be active, we need to determine the K value and see that whether that exceeds the expected fracture toughness values, in which case there will be catastrophic failure, or it is below the expected plane strain fracture toughness value, so that the leak before break condition can be applicable. So, Let us do a numerical to make this more clear. What it says is a titanium alloy which is used for a cylindrical pressure vessel which is having a diameter of 10 centimeter and thickness of 1 centimeter. The yield strength and fracture toughness of this material are 500 MPa and 25 MPa root meter respectively, and the component undergoes a safety test applying 50% of the yield strength before getting launched in market. So, this is very essential. Before something is being launched, it is always tested and tested at a condition which is more severe than the actual service condition. But before the safety test, it is found that there is a 2 millimeter deep semi elliptical flaw which exists normal to the hoop stress direction, and a design engineer is assigned to check whether the cylinder will survive the safety test. There is another part of this problem which says that during service only 50% of the stress is applied. The stress that is applied for safety test is being imposed. So, that means for the case of service, it is actually half of whatever has been applied for the safety test. And we need to determine the leak before condition, whether that will be applicable in service or not. So, let us first solve the safety test criteria. So, what it says is that the applied stress is 50% of yield strength. So, that means yield strength is 500 MPa, that gives to applied stress as 250 MPa. Okay. And we need to find out the K value as y1 y2 sigma root over pi a. A in this case is given as 2 millimeter deep. So, that is half the length of the minor axis. So, this is given as A equals to 2 millimeter. So, 2 into 10 to the power of minus 3 meter, and that leads to y1 as 1.12 because we are having a surface crack, and then y2 is 2 by pi because it is an elliptical one, and then we have sigma which is 250 MPa and pi into 2 into 10 to the power of minus 3. So, if we solve this quickly, we see the value as the following. Okay. So, this is coming as something like 14.1 MPa root meter. So, that means that the stress intensity factor value that is being generated for the safety test is much lesser than the K1C value, which is 25 MPa root meter. So, obviously, this means that it will survive the safety test. Okay. So, that is for sure that it is not going to break down at the safety test, although there is a flaw which is 2 millimeter deep and semi elliptical. Now, let us check the condition of leak before break for the service. So, in case of service, it is seen that the stress applied for service is actually 50% of that used for safety test. So, that means it is 125 MPa, and if we want to see the leak before break condition, we typically need to find out the K for this case. So, it says sigma root over pi t. So, sigma is 125 and t is 1 centimeter. So, that makes K value of around 22.1 MPa root meter. So, we see that leak before break condition will be applicable because this value that is generated is less than the K1C. So, it will fracture at the point of contact, at the leakage point, that will lead to the leakage, but the margin is very low because K1C is only 25 MPa and we are getting a value of 22 MPa. The margin is really close, and that should also be considered while using this in service. Okay. So, let us move on to another real life example where the concept of fracture mechanics is very helpful. So, these animals here are known as manatee, also known as sea elephant, sometimes as sea horse. These are found in the Sea of Florida, and these are giant animals, very big, something like of the size of around 200 or 240, 250 centimeter. Okay. But these are being constantly killed by the watercrafts, water vehicles that are used on that waterways. For example, the steamers, the small ships or the cruise, they simply hit this animal and their bones get fractured, particularly their rib bones get fractured and they die. So, there has been a lot of initiative to find out that even the path of the watercrafts or their speed limits, the kind of stress that they can generate, to figure out a way to save these animals. Okay, so let us see how we, while talking about fracture mechanics, how we can use our knowledge to be of little help. So, what we are seeing here is the internal structure of the manatee bone structure, and what we are seeing here is the rib base. So, there are around 17 to 19 pairs of rib bones in the different parts, and people have done some testing to figure out that how impact with the different watercrafts that is happening with these ribs, how can that lead to fracture and what is the typical fracture toughness of their bones. So, these are some of the fractographies from the fractured rib bones, and what from there itself we can figure out their fracture toughness values, because otherwise their bones are actually a compact one compared to human bones, and they also have some pores in their bones, and that leads to the failure, that acts as the crack or the defects that leads to the fracture. So, right after the fracture has happened, we need to figure out from the fracture surface itself that what has been the impact, how much load or how much stress or what would have been the stress intensity factor or fracture toughness that might have led to the fracture. So, this is once again a post-mortem study for the failure analysis part. So, from this images here you can see that the crack initiation or the fracture initiation site is somewhere near the surface. Okay. Here it is very clearly we can see that there might have been some kind of defect of this semicircular or semi-elliptical origin that might have led to the fracture. And to solve that, here is one more example or a numerical through which we will see that how much could be the fracture toughness, estimated fracture toughness of this manatee bone. So, it says this Florida manatee, which is having a scientific name like this, an endangered aquatic mammal, often gets killed in collision with the watercraft in the Sea of Florida. And failure analysis of one of this manatee rib bone revealed a semi-elliptical surface flaw of total major and minor axis of 4 millimeter and 1 millimeter respectively. So, such flaw size we can very well determine from that semicircular or semi-elliptical size that we have seen here. We can determine the major axis and the minor axis very well. Okay. And computational study is used to determine the stress that has been implemented on the manatee rib bone causing the fracture, and this stress that has led to the fracture turned to 200 MPa. What we need to find out is the fracture toughness of the manatee rib bone. So, what we have here is so that means that A C, which is given by root over A dot C, will be root over 2 into 10 to the power of minus 3 into 0.5 into 10 to the power of minus 3 Okay. So, that comes to very simple. So, that comes to 1 millimeter. Okay. What else we have is the applied stress, which is 200 MPa, and what we need to find out once again is K, which is related to y 1 into y 2 into sigma into root over pi a c. So, that comes to, this is once again a surface flaw. So, 1.12 into 2 by pi into 200 into root over pi into 1 into 10 to the power of minus 3. So, that turns out to something like this. Okay. So, it turns around 7.99, or let us approximate this as 8 MPa root meter. Okay. Fracture toughness values of manatee rib bone turns out to be 8 MPa root meter. Okay. But so, first of all we see that this value is quite less compared to the metallic parts that we were discussing so far, and all the other values that we have considered. The bones, typically in this case the manatee rib bones, has much lesser values of fracture toughness. But not only that, when we do this real calculations, and often found that these are again dependent on the size of the animal, the size of the bones, the impact, etc., lot of other factors that also need to be taken care of. But the point here was to discuss about this little offbeat topic is to see that how fracture toughness can be used, the concepts of fracture toughness can be used in the different aspects, something which is typically different from the structural problems that we deal with the industries. So, let us come to the conclusion for this lecture. What we discussed here is the effect of this multiplicity y factor due to the presence of elliptical or semi elliptical crack, and we have also considered or discussed about the leak before break condition and how that can be generated, how to take care of this factor while designing a component for such critical application. And the concept of fracture toughness is used for the failure analysis of manatee rib bone fracture. So, following are the references that has been used for this lecture. Thank you very much.